Now, in number 16, we have our last of the related rates application problems. You'll see here it says we have a rocket that's traveling vertically at a speed of 1,125 kilometers per hour. We know the rocket is the rocket is tracked through a telescope by an observer located 28 kilometers from the launch pad. Find the rate at which the angle between the telescope and the ground is increasing 2 minutes after liftoff. Determine the angle's increase in degrees per second. We had a problem just like this on Achieve, but Achieve lets you keep the angles in radians per hour, which is totally useless. So I'm asking you to convert that to degrees per second, which is a fairly easy final step in this problem beyond what Achieve wanted us to do. So now if we take a look at how this problem would be worked here, this is what I drew from the problem. We know that the person is sitting on the ground trying to track the rocket that's going up in the air, and the person is 28 kilometers from the base of the rocket where it went upwards. Now, we know that it goes upwards at a rate of 1,125 kilometers per hour. I had to go ahead and find out the height at the point of interest. So I know that the horizontal, it doesn't need a variable. He's always going to be a distance of 28 kilometers from the base of the rocket launching off. So that I didn't label X, I just labeled that 28 kilometers. I labeled the height Y because I know that the height is varying. Anything that varies must have a variable. Now, I solved for Y at the point of interest because I know I'm interested 2 minutes later. So I went ahead and said, well, okay, Y, distance is equal to rate times time. I have the rate, the time was 2 minutes, which is 2/60ths of an hour. And so I can say, well, if they're going 1,125 kilometers per hour for 1/30th of an hour, then they have went a distance of 37.5 kilometers. I went ahead and labeled the height. Now, as soon as I did that, I went ahead and just found the diagonal to this triangle. I wasn't sure I'd need it. It actually does come in handy later. But I know that the diagonal at the point of interest, since it's going to be the hypotenuse, is just the square root of 28 squared plus 37.5 squared. And when I did that, you can see I got the square root of 2190.25. And I just left it like that, so it'd be a nice exact answer. And anything that varies needs a variable. Well, I'm going to label that Z because I know that the length of that hypotenuse is going to vary as the rocket keeps on going up. But now keep in mind, I'd like to avoid having that hypotenuse in any calculations for the very simple reason is I don't know what dz dt is. I know what dy dt is, it's this, but I do not know what dz dt is. Now, the goal of the problem is to find out how fast this angle theta needs to rotate, find the change in theta with respect to time at 2 minutes. So at 2 minutes and the rocket's going up, how fast is that telescope going to have to rotate in order to keep up with the path of it? Well, here's my thinking here. I went ahead and said I need an expression involving the angle theta, and I would rather it not involve the hypotenuse since I don't know the hypotenuse's rate of change. Well, that simply only left me the tangent function since the tangent is equal to opposite over adjacent. That's y over 28 in this problem, which simplifies down to be 1/28 y. Now I can say, okay, I can take the derivative of that expression. Derivative of tangent is secant squared. And then we say chain rule says now we need to multiply by the derivative of that angle, derivative of theta with respect to time, d theta dt. On the right-hand side, the derivative of 1/28 y with respect to t is just 1/28 dy dt. At that point, once you take the derivative, you should be able to plug everything in and solve for d theta dt. So the first thing is I needed to put in what is secant squared theta. So in my head, I just thought, well, okay, secant, that's the reciprocal of cosine. Cosine is the ratio of adjacent over hypotenuse. So secant would be the ratio of hypotenuse over adjacent. That's what I did. Hypotenuse over adjacent, since it's secant squared, I have to square that group. This takes care of my secant squared theta. Now d theta dt is what I'm looking for. On the right-hand side, I had 1/28 times dy dt, and I know dy dt, it's increasing at a rate of 1,125 kilometers per hour. So d theta dt is going to equal that 1125 over 28. And then I just said, well, in order to get rid of this, I'd multiply by its reciprocal on both sides. That's why you see a 28 squared in the numerator here, and the 2190.25 without the square root in the denominator, because the square got rid of the square root. So then I entered that into my calculator, and I knew that my units would be in radians per hour. Whenever you're solving for an angle in any problem, it's always going to be in radians. And we know that the unit of measure of time in this problem was in hours. So we get 14.3819 radians per hour. That's not particularly very helpful. So I ask you to change that to degrees per second. So I take my radians per hour answer, and I can say, well, I need to do some unit conversions. I need to get rid of hours in the denominator. So I multiply by 1 hour. I divide by its equivalent in seconds. We know there's 60 minutes in an hour. There's 60 seconds in a minute. 60 times 60 is 3,600 seconds per hour. And then for the next one, I need to get rid of radians. So if I divide by pi radians to get rid of that radians, I need to multiply by the equivalent of pi radians, which is 180 degrees. So you simply take your 14.3819, you'll multiply it by 180, you'll divide it by 3,600 pi, and when you do that, you should get that this is approximately 0.229 degrees per second. And that makes a lot more sense to us rather than the 14.3819 radians per hour. You can actually see, okay, it's going to raise 0.2219 degrees per second. So approximately about every 5 seconds, or about every 4.5 seconds, it's going to increase a degree in order to keep up with the path of the rocket at this instant in time. Okay, up next, it's kind of anticlimactic once we move away from the related rates problems. The next ones are not as fun. Number 17 here, it asks us to estimate the change in y using differentials. And you're told that y is equal to the natural log of x, a is equal to 2. Please remember, a is just the specific value of x that you're interested in. And then the change in x is 1. So what this is actually asking us to do is it's saying use differentials to tell you what approximately the y values of the natural log of x change from as we go from the natural log of 2 up to the natural log of 3. So if you wanted to find the exact value, you could just go to your calculator and say, well, this is just the natural log of 3 minus the natural log of 2. And that should be approximately what we're going to get. Now, whenever we do the differentials to approximate, we just say, well, okay, here's my function, y in terms of x. I take the derivative. dy dx would equal 1 over x, the derivative of the natural log of x. So that tells me that dy is equal to 1 over x, and this dx can literally be multiplied on this side. And I would say dy is equal to 1 over x times dx. Now, what this implies is that the change in y should be approximately equal to 1 over the x value times the change in the x value. Now, dy and dx are the infinitesimally small change in y and the infinitesimally small change in x. That's why this is an equation, this is an approximation. So I can say, well, okay, let's see if that approximation is going to be valid in this case. We can say the approximate change in y should equal the x value of interest here is 2. So I can plug in 1 over 2 times the change in x, 1. And I get that the change in the y value should be approximately 1/2. Now, if I wanted to check that, all I would have to do is go in and say, well, in this problem, I need to understand what this differential is trying to get me to do. It's trying to have me estimate the change in the y values of the natural log of x as x moves from 2 to 2 plus 1, which is 3. So I could just say, well, okay, then the actual change in y is going to be the natural log of 3 minus the natural log of 2. Boom. Yeah, that's pretty close to 1/2. Now, in this case, if we were doing our error and percentage error, you get a fairly significant error on this, but I don't ask that on the test. So I just ask for what the change in the y value here would be, and we've got it. Now, number 18. It's asking you to use this same idea of linear approximations to find a linearization for the function f of x is equal to cosine x at a is equal to 3 pi over 4. So we're going to find the linear function that fits through the cosine of x at 3 pi over 4, the best possible one. So you say, all right, the linearization formula every single solitary time is the function evaluated at the x value of interest, which we call a, plus the derivative evaluated at the x value of interest, which we call a, times x minus a. Obviously, in this case, a is equal to 3 pi over 4. So all I need to do is evaluate my function at 3 pi over 4, add that to the derivative evaluated at 3 pi over 4 times the group x minus 3 pi over 4. And this will give me my linearization function of this. It's also, if you just want to think about it in terms as this is the equation of the tangent line at x equals 3 pi over 4, if you want to connect it to things we did earlier in the class. But now we can just say, well, we have this, we know we need to find these two things that are extremely easy to find. F of 3 pi over 4, plug 3 pi over 4 into your function f. It's the cosine at 3 pi over 4, cosine of 3 pi over 4, negative root of 2 over 2. What about f prime of 3 pi over 4? Well, I take the derivative of my function. Derivative of cosine is negative sine. Well, and then if I plug 3 pi over 4 into the derivative negative sine, I know the sine of 3 pi over 4 is the square root of 2 over 2. But then the negative out front makes it the exact same thing up here, and I get another negative root of 2 over 2. So for my final linearization answer, I would say my answer is f of 3 pi over 4. That's my negative square root of 2 over 2, plus the derivative evaluated at 3 pi over 4, which was another negative square root of 2 over 2. That's why I put minus square root of 2 over 2 times the group x minus a, x minus 3 pi over 4. Final answer. Up next, this is where we start doing the extreme value theorem test. Oh, sorry, no, this is not extreme value theorem. I need to make sure I read the test. This is Rolle's theorem. Number 20 is extreme value theorem. So Rolle's theorem is just saying that if you have a function on an interval and the y value is at the exact same point at the beginning of that interval and at the end of that interval, then you know that there exists some x value in between that beginning point and that ending point where the derivative is equal to 0. That has to be the case. So we're just going to verify Rolle's theorem in this problem. And I can say, all right, so the function I'm giving you, x squared minus 10x plus 9, and the interval's 3 to 7. So first of all, you need to show that Rolle's theorem applies. We do that by evaluating the function at the beginning and ending point. F of 3 gave me a negative 12. F of 7 gave me a negative 12. So I can say, okay, Rolle's theorem should apply. Now, what Rolle's theorem is going to say is that there has to be some x value between 3 and 7 where the derivative is 0, since this function begins and ends at the exact same y value. I take the derivative of my function very simply, and it's 2x minus 10. I set it equal to 0. Obviously, that gives me 2x is equal to 10, and x is 5. So now, the conclusion I can say up here, since f of 3 is equal to f of 7, Rolle's theorem states that there exists an x between 3 and 7 where f prime of x is equal to 0. Well, we have verified it. So that's what I put here. We can see that this occurs at x equals 5. 5 is between 3 and 7. So Rolle's theorem is verified. Pretty nice verification Shouldn't be any harder than that on your actual test. Now to the problem that I was thinking that one was, your extreme value theorem problem. So number 20, I'll give you a polynomial function on a closed interval, and I will ask you to determine any maximum or minimum values. And what the extreme value theorem says is that, well, the maximum or minimum values, they're at the endpoints or at any critical points within those endpoints. So I go in here and I can say, well, all right, I take the derivative of my function, and that's pretty easy here. I can just get my the 4 and the 1/4 cancel, and I'll get 1x to the third minus 1x squared minus 2x. At that point, I knew I needed to set that derivative equal to 0, so it would suit me to try to factor it. I factored out a common factor of x, and I got x times x squared minus x minus 2. Then I said, ooh, that trinomial is further factorable, factors of -2 that sum to get to -1, -2 and 1. So I get x times x minus 2 times x plus 1. I set that equal to 0 to find the critical points. Here, each of your factors set equal to 0. We're going to have critical points at 0, 2, and at -1. And unlike a lot of problems, every single one of the critical points that you can find are inside of your endpoints. So I can say, well, they're all valid for consideration then. So I went in and I said, I need to test my endpoints and every critical point within them. So I went in order, -2, -1, 0, 2, and then of course the last endpoint of 3. I just plugged them into my calculator, and when I did that, let's see if I still have it in here. I do. When I did that, I just entered my function into y1 here, and then as long as you have your table set up to where the independent is on ask, you'll be able to go to your table, enter in the x values that you want. Of course, you don't need the y2, it's just the y1 that we're looking at here. But you can see all of the x values, their corresponding y values, and then you just say, well, clearly the highest y value is where the maximum occurs, and the lowest y value is where the minimum occurs. And I went ahead and said I have a maximum at the ordered pair -2, 7.6 repeating, and a minimum at the ordered pair 2 and 2.3 repeating. Pretty nice. Now, number 21 and 22, get into our first and second derivative test, where we're trying to find intervals of where the function is increasing, decreasing, and any maximum or minimums in the first derivative test. And then the second derivative test would determine intervals of concavity and inflection points. So I gave you the exact same function, h of x, to work with both problems. For 21, where we're doing the first derivative test, you just say, okay, I take the derivative once. I know I need the critical points, so it would make sense to factor that derivative that you get whenever you can. And it was easy here. I just took a common factor of x squared out. My remaining factor is x minus 4. We set that equal to 0. So your critical points are going to be at 0 and at 4. Those are the values where your first derivative is equal to 0. So we can say, well, okay, those could also be the values in which my function changes from increasing to decreasing, or vice versa. So I have to break up the domain of the original function, which would be all real numbers since it's a polynomial, with these two critical points. I go -infinity to 0, and then 0 to 4, and then 4 to infinity. I choose test points within each of the intervals. Nothing special about these values other than they are inside of the region they're supposed to represent. Now, I plug these test points into the factored form of the first derivative. And I can say, well, okay, when I plug a -1 in here, well, -1 squared is positive, -1 minus 4, negative. I know that a positive times a negative is a negative. And whenever the first derivative is negative, you know your original function is decreasing. So I already know h of x decreases from -infinity to 0. Now, what about my next region? Well, I'm using a 1 to represent the values between 0 and 4. When I plug a 1 into the first factor, still positive. When I plug a 1 into the second factor, 1 minus 4, still negative. So nothing changed at this critical point at 0. The derivative was negative before 0. The derivative is still negative after 0. And I can say, well, h of x is still decreasing. This is going to be a function that decreased before 0 and decreased after 0. And then it's going to continue to decrease probably until I get to this critical point at 4. What happens between 4 and infinity? Well, I'm using a 5 to represent that region. When I plug that in, of course, again, the first factor is going to be positive. The second factor, 5 minus 4, would also be positive. The product of two positives gives us a positive first derivative. So I'd say I'm supposed to remember whenever the first derivative is positive, the original function is increasing. So the original function is going to be decreasing from negative infinity to 0, union 0 to 4, but then it's going to be increasing from 4 to infinity. And now, since it decreased all the way until 4, I know 4 is the location of a minimum. And then it's going to increase after 4. You're not going to have a maximum. 0 is neither a maximum nor a minimum because it decreased before and it decreased after. Now, whenever you have a critical point that's not a maximum or a minimum, you're already guaranteed it is an inflection point, but I don't ask that in 21. That's what 22 shows us. In 22, we take the second derivative of our function. My second derivative here would give me 3x squared minus 8x. When we factor that, we can factor an x out and get x times 3x minus 8. When we set those factors equal to 0 to find potential inflection points, we can say, well, we have a potential inflection point when x is 0 and a potential inflection point when 3x is equal to 8, gives me x equals 8/3. So just like my first derivative test, I break up my second derivative test, the domain of the function, with these potential inflection points. From negative infinity to 0, and then from 0 to 8/3, and then from 8/3 to infinity. I chose a -1 to represent the first region, a 1 is in the middle of the second region, and then 5 is certainly in the last region there between 2 and 2/3 and infinity. Now I put my factored form of the second derivative here for the test, and all I'm concerned about is the sign of the second derivative. Whenever the second derivative is positive, the original function is concave up, it's U-shaped. Whenever the second derivative is negative, the original function is concave down, N-shaped. So now when I plug the -1 in here, the first factor would be negative. The second factor, you'd get -3 minus 8 would be a -11, but the product of two negatives is a positive. Whenever the second derivative is positive, the original function is concave up. Now for that next region, I'm using a 1 to represent it. So my first factor would be a +1, but my second factor would still be a -5. Positive times a negative is a negative. Thus, my original function is concave down in that region. And then lastly, with the 5, when you plug a 5 in, both of your factors would be positive. You'd have a +5 times a +7. Our product would be positive, tells us our original function is concave up. Now, the only thing I'm asking in 22 are what are the inflection points and what are the intervals of concavity. If you show your intervals of concavity like this, that's fine. You don't need to write any more. But then you can say every potential inflection point was an actual inflection point. Did it change concavity at 0? Yeah, it went from concave up to concave down at 0. Did it change concavity at 8/3? Absolutely. It was concave down before 8/3, concave up after 8/3. So inflection points at both of the potential inflection points, 0 and 8/3. Now, 23 gets into the L'Hopital problems. Now, what I guarantee you is your test will have 4 L'Hopital problems, very similar to how this practice exam has it. I promise you, in one of the 4 problems, you should not use L'Hopital. That's one of the things I'm wanting you to be wary about. A lot of people, whenever they see a limit, they just start taking the derivative of the numerator and denominator without even thinking. With L'Hopital, you need to remember in fractional form, it needs to be indeterminate. meaning it's 0 divided by 0 or infinity over infinity. If it's not one of those two cases when it's in fractional form, L'Hopital does not apply, and L'Hopital will lead you to a wrong answer. So please be careful as you work these problems out. Again, one of them you should not use L'Hopital at all. So as we go through these, we'll be thinking about that. Number 23, I have the limit as x approaches 0 of 1 minus cosine over x plus x squared. Clearly, L'Hopital does apply because if I try to plug in a 0, my numerator is 1 minus 1. My denominator is 0 plus 0. So I get 0 over 0. That is indeterminate. L'Hopital should be able to help. Anytime you use L'Hopital, notationally, you're supposed to put an h over the equal sign, and then say, now this is going to be the limit as x approaches 0 of, this is the derivative of the last numerator, derivative of negative cosine is positive sine. Derivative of your denominator, you're going to get a 1 plus 2x. But now at this point, you're done. And the reason you're done is because of what I was just saying about L'Hopital. L'Hopital only applies when it's 0 over 0 or infinity over infinity. If you try to plug in your 0, yeah, your numerator is 0, but your denominator is not. It's 1 plus 2 times 0, so your denominator is 1. As soon as that denominator is no longer 0, you're done with this problem. 0 divided by 1, final answer of 0. Now, please do note, if you use L'Hopital again, thinking, it's not going to hurt, it would definitely hurt. It would lead you to a numerator of cosine x and a denominator of 2. When you took that limit, it would give you an answer of 1/2, which is an absolutely wrong answer for this problem. So please don't think, oh, it doesn't matter. As long as I take the derivative correctly, L'Hopital is going to work. It will not work. So only use L'Hopital when it applies. I go to 24. We have the limit as x approaches 0 of the square root of 1 plus x minus 1 minus x over 2 divided by x squared. So I thought about this. Can I plug in the 0? My numerator would be square root of 1 minus 0. That's a 0. My denominator would be 0 squared. 0 over 0, L'Hopital applies. So now this becomes the limit. I thought of that first group as 1 plus x to the 1/2 power. So the chain rule would tell me that 1/2 power comes down in front of the group raised to the 1 lower power, technically times the derivative of the inside, but that's just a 1, so I didn't have to worry about that. Derivative of the second term became 0. The last term, I thought of that as minus 1/2 x, and then the derivative of minus 1/2 x is minus 1/2. Derivative of the denominator, 2x. Now, if I tried to plug in my x value of 0, your numerator would be 1/2 times 1 minus 1/2. That would give you a 0. Your denominator would be 2 times 0. So again, you have 0 over 0. One application of L'Hopital did not help. It's still indeterminate. Keep at it. So I use L'Hopital a second time. When I use L'Hopital a second time in my numerator, this negative 1/2 comes down, multiplies the 1/2. I get negative 1/4 times the group to the negative 3 over 2. That second term has a derivative of 0. My denominator has a derivative of 2. The instant I get that 2 in the denominator, I know I'm done because it's no longer going to be a denominator of 0. L'Hopital has done its course. So I plug in the 0. In your numerator, you're going to have negative 1/4 times 1. Doesn't matter what power 1 is to, it's still a 1. So negative 1/4 times 1, that's negative 1/4. Negative 1/4 divided by 2 is negative 1 over 8. And if you get that answer, you'd be doing great. For number 25, we say, well, okay, here we have the limit as x approaches 0 on the right-hand side of the square root of x natural log of x. Now, this is not in the natural form of L'Hopital. L'Hopital requires fractions. If you try to think about this, though, you just say, well, this is a number approaching 0 times a number approaching negative infinity. That is one of our indeterminate forms that L'Hopital should be able to handle, but it can't even begin to handle it until you get it into a fractional form. So I was thinking about this and saying, well, it'd be a lot easier to move that x to the denominator, since that's x to the 1/2 power, and call it x to the negative 1/2 power, rather than moving the natural log of x. So what I have here is equivalent to what I have here. Now this is in the format, since it's in fractional format, where L'Hopital can help. And if you tried to apply the limit in this point, natural log of a number approaching 0 from the right, that's your negative infinity. Your denominator is 1 over the root of x. And as that's approaching 0, that would be approaching infinity. So this is a negative infinity over infinity at this point. I use L'Hopital since that's one of our indeterminate forms. When I do that, my derivative of the numerator is just 1 over x. The derivative of the denominator, power rule, you'll get negative 1/2 times x to the negative 3 over 2. And then what I did here is I just wanted to clean this up. I could see that I had x to powers in both the numerator and denominator. I wanted to get rid of the negative exponent in the denominator. I multiplied by an understood 1, perfectly legal algebraic maneuver. So in multiplying by that understood 1, that got rid of the x in the denominator altogether, and it just left me a denominator of negative 1/2. Now, do not put an h over this equal sign. I'm not using L'Hopital or anything in this step. I'm just rewriting an equivalency of my limit. So I still keep my limit notation as x approaches 0. My denominator is just going to be a negative 1/2. My numerator, this is understood to be x to the negative 1. Well, x to the negative 1 times x to the 3 over 2 would be x to the negative 1 plus 3 over 2 power, gives me x to the 1/2 power. Then I can say, at this point, as soon as that denominator is no longer infinity or 0, I knew I was done. So can I plug 0 in for x? Sure you can. When you do, your numerator is a 0, your denominator is a negative 1/2. 0 divided by any finite number, still 0. So that's a good problem. Now you might be thinking, wow, all three of these, he's used L'Hopital. So I bet 26 is the one where he should not use L'Hopital. If you're thinking that way, you're thinking correctly. Now, I did go ahead and do something in 26. I really didn't even have to do this. You could have just looked at 26 and said, John, that's not indeterminate. 1 over the cosine of 0, that's 1 over 1. And then this is minus 1 over e to the 0, which is also 1. 1 over 1 minus 1 over 1. Your answer is 0. Done. Could have you just done that? Absolutely. There's no work that's needed in this problem. I wanted to go ahead and at least get a common denominator. Again, there's no need to do this. But in the first one, I said, well, I would need to multiply it by e to the x. I'd need to multiply the second one by cosine x over cosine x. And that gives me a numerator of e to the x minus cosine x all over my common denominator of e to the x cosine x. You didn't have to get the one fraction. I chose to. But now in this format, it would be important for you to understand, well, you still can't use L'Hopital. If you were going to use L'Hopital, you would get it into fractional form, one fraction, not two. So this would have been necessary if L'Hopital would have been necessary. But in this step, you just look at it and say, okay, is it 0 over 0 or infinity over infinity? Plug your 0 in. E to the 0 minus the cosine of 0 becomes 1 minus 1. Your denominator, e to the 0 times the cosine of 0 becomes 1 times 1. So you got a numerator of 0, a denominator of 1, you have an answer of 0. Final answer there. And again, this is one of these where if you tried L'Hopital, it's going to lead you to a wrong solution. Now, what I'm guessing, the problem that many people will maybe think is the hardest one on here, number 27, I think it's a cool problem. There was a problem out of the textbook homework assignment extremely similar to this. Sadly, I don't think Achieve had any fun optimization problems like this, but I do think it's a pretty cool problem. It says, find the minimum area enclosed by 25 meters of wire cut into 2 pieces, such that one of the pieces is used to construct an equilateral triangle and the other is used to construct a circle. what is the amount of wire that should be allotted to each figure to have the minimum total area? Okay, so here's my thinking about the problem. We know that we have a 25-meter wire. We're going to allot some of the wire to be used for an equilateral triangle, some of the wire to be used for a circle. So I went ahead and just said, well, okay, let's let X meters of the wire be designated for the equilateral triangle. And then since you have 25 meters of wire, then you're going to have 25 minus however much this is, X, left over for the circle. Now, I went ahead and thought about what the area of the equilateral triangle with a perimeter of X could be. I know if the perimeter is X, then every side of that equilateral triangle is going to be X over 3. Now, the entire base here would be X over 3, but half of that base would be X over 6. And the reason I drew this is because area of a triangle is always 1/2 base times height. Any one of these sides could be its base, but I don't have the height of it. These are diagonals. So I can say, well, I would need to find the height that I drew in there. That creates a right triangle within your equilateral triangle that would have a hypotenuse of X over 3 and a side of X over 6. So I said this height would equal the square root of the hypotenuse squared minus the other leg squared, X over 3 squared minus X over 6 squared. And then I knew X over 6 squared would give me X squared over 36. This would give me X squared over 9. I went ahead and got a common denominator. I know 9 times 4 is 36. So X squared divided by 9 is the same thing as 4X squared over 36. That enabled me to get a common denominator there of 36. And then I can subtract out and say, okay, then your hypotenuse is going to be the square root of 3x squared over 36. We know the square root of 36 is 6. I'll have the square root of 3 up here that doesn't simplify, and the square root of x squared just simplifies as x. So it's better if you'll write the height as, hey, this is my coefficient, the root of 3 over 6 times the variable x. That's the most efficient way of writing the height, because now I need to use that height back into my area formula. I know that the area is 1/2 base times the height. Well, 1/2 the base, any of the sides could be the base, it's x over 3, times the height, the square root of 3 over 6 times x. That's giving me the area of the triangle equal to the square root of 3 over 36 x squared. Now, I need the area of the circle. Well, I know that the area of the circle is pi r squared. I don't currently have the formula for the radius though, but that's easy to get because we know that the amount of the wire that we're going to use for the circumference of the circle going all the way around it is 25 minus x. So I set the circumference of the circle equal to 25 minus x, and I know that my circumference formula is 2 pi r. So 2 pi r is equal to 25 minus x. That means that r is going to equal 25 minus x divided by 2 pi. Now, once I have my equation for the radius of that circle, I can then go in and say, well, then the area of the circle is pi times that radius formula squared. Gorgeous. Now, what I did here is I just said, well, your denominator 2 pi quantity squared would be 4 pi squared. One of those pi's canceled out with a pi in front and just gave me a 4 pi in that denominator. Your numerator 25 minus x times 25 minus x is going to give you 625 minus 50x plus x squared. Now I chose to write that in descending order. I distributed that 4 pi into each one of these terms. The first term, you're going to have 1 over 4 pi times x squared. Second term, you're going to have minus 50 over 4 pi times x. And then, of course, your constant's going to be plus 625 over 4 pi. Put it in descending quadratic form. Now, that's nice because then I can say, okay, we need to minimize the total area from these two objects. Got the area of each object. I just add the two objects together. So I take this formula plus this formula. Both are going to be irrational coefficients, and I wanted to keep my answer as exact as I could. So I just went ahead and collected my two irrational coefficients in front of the x squared term. I said my total area formula is going to be the square root of 3 over 36 plus 1 over 4 pi, all times x squared. And then we have minus 50 over 4 pi x plus 625 over 4 pi. That would be my total area formula. Now, fortunately, we know that this is going to be an easy problem now. Why? It's a positive parabola. Every single positive parabola in existence has its minimum at its critical point, because the vertex is its critical point, and the vertex is going to be its lowest point. So all we have to do, take the derivative, set it equal to 0. That will be the value of x that minimizes this problem. Woohoo! Now, I go ahead and take the derivative. That 2 comes down and multiplies this. When it does, I just divide each of my denominators by 2. That's the more efficient way to do this. Of course, you could have said 2 on the root of 3 over 36, and then that reduces down to the root of 3 over 18. And we'd also have plus 2 over 4 pi that reduces down to 1 over 2 pi. So that's my new coefficient of x. And then my second term would just has a derivative of minus 50 over 4 pi. We set that equal to 0. When I do that, the 50 over 4 pi moved to the right-hand side. Then I solve for x by dividing by its coefficient. And when I did that, please be very careful about how you enter that into the calculator. A lot of students struggle entering this expression into their calculator. Make sure you can get this and get the 15.58 meters. Now, if you have the fraction buttons on your calculator, it really saves you from doing a lot of parentheses. Otherwise, you're going to have to put parentheses around the 4 pi, parentheses around the 2 pi, and of course, parentheses around that whole group. But what I would do here is I would just say, okay, I have the fraction, and then I'll go ahead and 50 over my 4 pi. And then we're saying that entire fraction divided by the group, and I'll do fraction again here. We have the square root of 3, and that's over 18, plus 1 over 2 pi. So plus, and again, I'll use fraction, 1 over 2 pi. But again, I can't reiterate enough. If you're not using these fraction keys on your calculator, you would absolutely have to put 2 pi in a parentheses. Otherwise, you would be dividing 1 by 2 and then multiplying that answer by pi, which is not what you want here. This should be the answer I got. Gorgeous. Now, make sure you're answering the question. I would tend to get happy with that 15.58 and might stop there. I can't stop there. My problem on the test specifically asks me, what is the amount of wire that should be allotted to each figure? So, well, X, that's the amount of wire that should be allotted to the equilateral triangle. So I said, okay, this is telling me 15.58 meters for the equilateral triangle. And then I just said 25 minus 15.58 is going to give me 9.42 meters left over for the circle. Gorgeous. Your next problem is about finding the point of maximum profit. We have a problem given that says a manufacturer estimates that when X units of a particular commodity are produced each month, the total cost will be C of X is equal to 1/3 X squared plus 5X plus 409. And all units can be sold at a price of $699 minus 3X dollars per unit. Determine the price that corresponds to maximum profit. Okay, so what I would do in that problem, we know that profit is always equal to revenue minus cost. But now please remember, the revenue in this problem, it's going to be determined by the number of units you can sell times your price function that sets the price at which you're going to sell each unit for. So X times P of X is going to be the revenue function. But now the cost function already takes into concern how many items you're creating. So You don't need any x times c of x there. It's just x times the price function minus your cost function. Okay, so your profit function is x times the price function mentioned in the problem minus your cost function. Now, when I simplify this, I would get a negative 3x squared minus 1/3 x squared, gave me negative 10/3 x squared. I'd have 699x minus 5x for 694x. Then I would have minus 409. Now, similar to the last problem, this is going to be very easy at this point. He's like, well, what do you mean it's going to be very easy? It's a negative quadratic. Every single negative quadratic in existence has a critical point that's going to yield a maximum. So I just say, okay, all I have to do is take the derivative, find that critical point, and that's going to be the point that maximizes profit. So the derivative here would give me negative 20 over 3x plus 694. We set that equal to 0. You'll get 694 equals 20 over 3x. Thus, x is equal to 694 times 3/20ths. And then you say, well, 694 times 3 over 20, that's going to give me 104.1. But now you need to understand X is the number of units you should produce and sell in order to maximize profit. It doesn't make sense to say, oh, I'm going to create 1/10 of a unit. No, you're going to create a whole number value of units, and you always just round to the nearest value. So since X is the number of units you should produce and sell, that means we should produce and sell 104 units, not 104.1 units. Now, the profit occurs when 104 units are produced and sold. That's still not answering the question, though. The question was, determine the price that corresponds to maximum profit. Well, right here's your price function. So then I can say, okay, whoops. I can say, okay, I'll go to my work. I'll go to my price function and say, the price would be, your price function was right here, 699 minus 3 times the x value of 104. It's telling you should charge $387 a piece in order for you to sell 104 units and make your maximum profit. Okay, now number 29 builds off of that problem. You can see it's just asking us to find the minimum average cost of the cost function given in that last problem. So the only thing I need from the last problem is that cost function that's mentioned in it right here. And then I can say, well, if that's the cost of X items, then the average cost per item would be my cost function divided by the number of items, which there are X items. So I can say the average cost function every single solitary time is nothing more than your cost function divided by X. When I distribute that X into each term in your numerator, you'll get 1/3 X plus 5 plus 409, and I went ahead and called it X to the -1 for that last term. Now, when I take the derivative of the first term's 1/3, second term cancels out, third term is going to give me minus 409 X to the -2. That's easier to solve if you get rid of the negative exponent, so I went ahead and rewrote that as 1/3 minus 409 divided by X squared. Now we set that equal to 0 to find the critical point. When I do that, I'll get 1/3 is equal to 409 over X squared. Then when I cross multiply, I'll get X squared is equal to 3 times 409, which is 1227. Took the square root of 1227, gave me 35.029. Now, just like in 28, X is representing how many units you should produce, in this case, in order to create the minimum average cost. You're not going to have the lowest average cost if you're creating a part of a unit that you can't even sell. So you always want to round X to the nearest value. You should produce 35 units in order to create the minimum average cost. But again, 35 is not the answer to the question. 35 is the number of units that you need to use in order to produce the minimum average cost. But the answer to the question is to find the minimum average cost. So you say, okay, I'll take that that x value that minimizes the average cost function, and I'll literally plug it into my average cost function, which was right up here. So I need to evaluate the average cost function at 35. So I've got 1/3 times 35 plus 5 plus 409 divided by 35. Now, I know that this answer is going to be in dollars, and it's, in fact, the cost function was in dollars, x was number of units, so this is going to be the number of dollars per unit. This process would have a minimum average cost per unit of $28.35 per unit. Now, this is a pretty fantastic business if you're just looking at markup on an individual item. Keep in mind, this is telling us that their minimum average cost is $28.35 per unit, but their goal is to sell them for $387 per unit. If that's the case, then they're making over $350 profit per unit. That would be a phenomenal business plan if that were possible. But the answer to this question, the 2835, is what I'm looking for. Now, your final two problems, Newton's method. In number 30, I just ask you to use Newton's method to simplify the square root of 133. So you start off by just saying, let x equal the square root of 133. Now, we know Newton's method has to be an equation set equal to 0 that has non-constant derivatives. So you say, well, all right, this isn't going to cut it. So I go ahead and first thing I do is I square both sides. If x is equal to the square root of 133, then x squared is equal to 133. Then my function that I can set equal to 0 would be f of x is equal to x squared minus 133, and the derivative of that, 2x. Now I can say, okay, I have my function, I have the function's derivative. In this problem, I ask you to start with an initial guess of an 11, and I said go until you're certain that you have 4 decimal place accuracy. So to show the Newton's method here, I could go in and say, well, all right, I'll put that 11 in as an answer. I will then store that answer in as my variable x, and then go colon, type in Newton's method. It is always x minus f of x divided by f prime of x. So x minus f of x in this problem was your x squared minus 133. So I'll create a nice fraction here and say x squared minus 133. Oh, it's hard to type this in when I'm not looking at the calculator. I probably need to look down. And then we'll divide that by 2x. And again, this is the type of problem where if you're not using the fraction like I'm using here, you would have to put parentheses around your 2x. This looks good. I'll go in and say, okay, where's my first refined guess? And that's where I put this in. So 11.54 repeating. My second refined guess, I got the 11.53256979. At this point, I wasn't even guaranteed 2 decimal place accuracy because it did not repeat to there. So I kept going. And by the third refined guess, I had 11.53256259. And I knew I could stop there because I said I wanted you to have 4 decimal place accuracy. Please notice here, even though the 4th decimal place, well, actually, to 4 decimal places, you're fine in this one. It's 5.3. It would round up to 2.6. 5.3. This one would round up to 2.6. In fact, it's very close even after that. But I only asked for a 4 decimal place answer, so I can say I have conclusively arrived at that answer by the third refined guess. I can stop there and say that this is approximately equal to 11.5326. Now, for the next problem, I ask you to find the root of the cubic equation x cubed equals 5x minus 8 using Newton's method. Newton's method requires a function set equal to 0. So I went ahead and moved the 5x and the 8 over with the x cubed and said f of x is going to equal x cubed minus 5x plus 8. And then f prime of x would be 3x squared minus 5. Now, the given value in this one, it said start Newton's method with an initial guess of -2. So I would go in here to my calculator and say, okay, if I start with an initial guess of -2, I'll go -2, get that in as an answer. And then I'll say, okay, I'll store that answer in as x. If I lift my calculator up. I'll store that answer in as x and then alpha decimal to bring in the colon. Type in Newton's method. It is always x minus f of x. And this time I'll do it as if I don't have the fraction sign on my calculator. It's no big deal. I'll just say f of x, which is the group x raised to the third minus 5x plus 8. Close out that group. Since I didn't use the fraction, I would have to divide by the group 3x to the second and minus 5. And I'll close out that group. Doesn't look as nice. I prefer the look of the fraction, but this will be the exact same thing. My first refined guess, I get the -3.42857. That's -3 4/7 if you wanted a fraction, but -3.428571429. So I can say, okay, I've got that in. Clearly, I have no decimal place accuracy whatsoever at this point. My second refined guess, and I want you to put in every single one of these. So everything I'm writing here, I would want you to write on the test. My third refined guess. And at this point, I actually started to worry a bit because I was like, wow, I'm to the third refined guess and it hasn't even agreed to 1 decimal place. But I kept going. Your fourth refined guess. And here I was like, oh, okay, now things are starting to converge. I've got -2.80260828. And I can say, well, still, I don't quite even agree to 2 decimal places because this would be -2.81 and this would be -2.80. So I kept going again. And by the time I got to my fifth refined guess, I was fine. And the reason I'm fine here is because please notice this would be -2.8026. Well, this is -0.80. Even though it's 2.5, that 8 would round that 5 up to a 6. So you say, well, the 4 decimal places, this and this are the exact same answer. So you can stop. You can say it is converged to 4 decimal places, and our convergent answer is -2.8026. Now, if you wanted to go again, which there is no reason to, but if you wanted to, you can already see that this was actually correct out to what 8, 9 decimal places, but we only needed the 4, so that's why I stopped my answer at 4 decimal place accuracy there. All right, guys, know that this is a long test. I will do my best to give you as much time as you need on it. I'll also be very, very kind as I'm grading this. So please just do your best and know that I'm here to help out in any way. Let me know if you have any questions, and I look forward to seeing you on the test day.